Now, the last time we were talking ethereally about what's happening in a circuit. We were trying to go through the whole idea of the electrons moving through the wire, their mean free path, or the distance that they travel before hitting another object, their drift velocity, and things like that, how long they move, how long it takes them to move through the wire. That stuff's great, but as a theoretical application goes, you're probably never going to be asked questions related to that. Now, we will come back to that microscopic view again in a couple days when we talk about current density and resistivity. But Kirchhoffs laws are pragmatic. They're not microscopic, they're macroscopic. They look at the circuit. But before I launch, I want to make sure you have three things in your notes. The charges travel on the outside of the wire because all excess charge is on the outside of a conductor. This is big in your book. Your book devoted an entire chapter to it. I read it. I don't like it. Still don't like your book, but it doesn't matter. So the first thing is that it is the electric field that pushes the charges around. And the charges establish a steady state motion almost immediately upon closing the switch. What? Meaning they reach a point where the net force is zero almost immediately upon closing the switch. Your book suggests that it's 10 to the negative 9th seconds is the kind of time span we're talking about between when the switch is closed and the steady state motion of the particles is occurring. All right, so here we go. Kirchhoffs laws. The first one is the voltage drops through any closed path through a circuit is zero. The voltage drops through any closed path through a circuit is zero. I will call this the voltage rule. I won't say Kirchhoffs laws. The second one is the current rule, and it's the current into any junction must equal the current out. Now, although these are called Kirchhoffs laws, please understand that today we really understand these in a different way. The first law is conservation of energy. It was not fully known that we were talking about the energy of the charges back when Kirchhoff did his work. The second one is conservation of charge. It just comes down to that. Now, we will have to be more careful this year than we have in last year because we will have voltage supplies in our loop and we might have more than one. So from this point forward, you're going to have to forget a few things from last year to understand that the direction of current is not arbitrary. Neither is the direction of your loop. When you are choosing to draw a loop through a circuit, you must indicate the direction that you are moving through that loop. What you are effectively doing is deciding the direction of positive current flow. So the first part of the rule is to draw a loop through your circuit. I almost always will start at the small side of your potential difference. That is the low side of the potential difference. The reason that's important is that when I begin my loop, I am going to draw a loop through the circuit And the direction that I've drawn that loop is telling me what I am assuming will be the direction of positive current flow. Now, when I draw this loop, I'm also making some decisions. The first decision I'm making is that this loop represents flow of current. But what I'm really interested is looking at that loop as a closed system where the voltage drops must sum to be zero. For resistors, that's easy. Regardless of the direction of the current, resistors will always have a voltage drop that is negative. But for batteries, it's not that clear cut. When you go from the small side to the big side of a battery, you are increasing potential, which means those voltages are added. When you go from the big side to the little side in your loop, you're going across a decrease in potential. Those voltages are subtracted. So to use this rule, we are going to sum the voltages, but you have to know when to make them positive and when to make them negative. So just right now, I'm going to say that this is voltage 1, this is voltage 2, and this is voltage 3. I did a bad naming convention here, so let's go over to my assigned voltages and switch them to A and B so I can separate them from the voltage drops across the resistors. I wasn't thinking too much in the future. So the red loop is what I'm going to call loop 1. When I pass through the circuit, all I'm going to say is VA minus V1 minus V2 equals 0. When I go through this loop, I'm identifying that the voltage drops in that loop will sum to be 0. I subtract voltage drops across resistors, but for voltage supplies, I add them or subtract them based on the direction of my assigned current. Now, this next part is going to be a little bit more difficult for you to understand. So I need to make sure when using Kirchhoffs laws that I draw a loop for every circuit element in the system. Now, in order to do that, I'm looking at my system and realizing I left out 2 elements with the loop that I chose. So I need to choose another loop. I think all of you would agree there's 2 possibilities of what I could choose to do. I could choose a loop that goes through here or a loop that goes around the outside. Neither of those makes a difference, which one I choose to do. I would encourage you to always try to make a new loop that agrees as much as possible with the direction of the arrows you've already drawn. I'll explain why in the future, but for me, I think the best loop would be to do one that goes across the outside. You'll notice that by choosing that particular loop, I get the benefit of having the blue arrows always in the same direction as the red arrows. Does that make sense? Bless you. Now, I could have chosen a loop like this, and that would have likely been similar. But I'm also trying to look at the future of what I need to do, and I'm recognizing that it is more likely that these blue arrows represent the actual direction the current's flowing because of where the batteries are. The batteries are pushing charges, this way and this way. So it's likely that I've drawn the arrows correctly. We might not get that option in the future, so when you get the option to be able to be in agreement, use it. So, loop 2. Noting from where I started, I will have VA minus V1 minus V3 plus VB equals 0. Any question about this yet? Now, there's no reason to do the other loop that has not been done. Once you've encountered and made sure you have a loop that uses every single circuit element, you're done with Kirchhoff's first law. But it's incomplete until you do Kirchhoff's second law. Kirchhoff's second law deals with junctions, to which I have 2. Now, junctions are a little bit weird and require that we understand something about a junction. First, for every one of these loops that we've drawn in, we've made an assignment for the direction of current through that resistor. For example, I have said that current must be passing this way through this resistor. I'm going to call that current I1. I've made a similar assessment here that current is passing this way through resistor 2. I'm going to call that I2. I've made another assessment that current is passing this way through resistor 3. I'm going to call that I3. Now, being a person of foresight, I1 must also be traveling through voltage supply A, for they are in series, and all things in series must have the same current. In a similar way, I3 must be traveling through voltage supply B, for they are in series, and all things in series must have the same current. This isn't part of the rule, but it's something you need to keep in mind when doing this. That elements that are in series still obey those rules, no matter how complicated the circuit is, no matter how many power supplies there are. And you need to leverage that information for what's going to happen next. I'm looking at this junction. I'm also noting that whatever that junction gives me for a relationship, this junction will be identical. Does everybody see why that has to be true? So you don't have to do this for every junction. When you notice that there's going to be 2 symmetrical junctions, just use one. So at this junction, the rule states current in has to equal current out. I see I1 going into that junction and I2 and I3 coming out of that junction. Would you guys agree with that? So I'll write that as I1 equals I2 plus I3. Any question about where these have come from? All right. Take a quick walk with me. Let's say that all the resistances were given and all the voltages were given. Let's count up all the unknowns. V1 would be an unknown. V2 is an unknown. V3 is an unknown. I1 is an unknown, I2 is an unknown, and I3 is an unknown. Kirchhoffs laws generated 6 unknowns and 3 equations. You understand it can't be solved now. We will need 3 more equations. Now we're going to get those because we know resistors obey Ohm's law, which means this generated 6 equations and 6 unknowns. So do you now understand why Diffenderfer likes to suggest there might be other ways to do this. All right. That's of very little use to you until you realize that there's going to be some other relationship here. Something that either brings a voltage and a current together or brings something else into the equation that you can use. Now, for resistor circuits, it's pretty easy. We're going to have Ohm's Law as a means of bridging the gap between the voltage portion of Kirchhoffs rules and the current portion of Kirchhoffs rules. If it's a capacitor circuit, we're not going to have that, but we don't have any current across any capacitors. We have charge instead. So for capacitor circuits, we don't use Kirchhoffs laws. We don't use the current law for Kirchhoff. We can only use the voltage law. But later in the year, we're going to have inductors, and inductors are like capacitors, except they store their energy in a magnetic field, not an electric field. So for them, they are current devices. So we would use an equation that has current in it. But ultimately, for every one of these voltages, there's a relationship between the voltage and the current. So looking at what we've got written here, let me get rid of these for just a minute. We can start adding to this. V1 equals R1 times I1. And V2 equals R2 times I2. And of course, V3 equals R3 times I3. And now you've got it. 6 equations, 6 unknowns. Now, let's be honest, this is still a monster. No matter what, this is going to be hard to solve. Even given all the resistances, you do understand why this is tough. But you can start diving in there. Generally, you start doing your substitutions. So you start looking at, VA minus R1 I1 minus R2 I2 equals 0. And VA minus R1 I1 minus R3 I3 plus VB equals 0. Then you start doing your substitutions with your currents. And you can eventually get down to a single relationship. But this is not easy. Which is why, like I said to you, even a simple circuit with 2 loops can become a mess really fast. Now, AP is not going to be about this kind of stuff. The AP exam isn't going to try and get you to spend 20 minutes on trying to solve 6 linear equations in order to get yourself an answer, which is what this is. This is a system of 6 linear equations. AP is going to be more about, do you understand what's happening due to Kirchhoffs laws? Now, you guys last year should have recognized that we did 2 different types of circuits when we tended to see these. First, there were the ones that generally had this look to them. Find the current and voltage through every resistor. Do you remember these? This is a standard stepwise reduction activity. It's a way around having to deal with Kirchhoffs laws. And for us, it's a pretty straightforward means to an ends. So be honest, how many of you could do what I just asked? Could find the voltage and current through each resistor? Who could deal with the refresher then? So I'm only seeing about 6 hands up. All right, let's do a quick refresher on this one. It's not a bad one to do. It's fairly straightforward. And as we look at stepwise reduction, the hardest part of stepwise reduction is the recollection of whether you're dealing with voltage or current when you step back through a circuit. This particular one isn't easy to see from the onset what's in series and what's in parallel. Stepwise reduction requires that you understand what's in series compared with what's in parallel. So I would probably redraw this and focus on making my circuit appear more oriented to series and parallel. Does this look easier? Hopefully it does. So looking at this circuit, I realize that the 3 and the 6 ohm resistor are in parallel with each other. So the first thing you do in stepwise reduction is you kind of make a road map. This is how I teach it in AP1. A road map that takes us from one circuit to a simpler circuit in a series of steps, reducing the circuit a little bit every time. Stepwise reduction. You'll notice I don't draw the whole circuit. I just draw the resistor portion. So this is going to be my road map. And in reducing the circuit first, I'm going to reduce the parallel element. It is incumbent upon you to know the rules for series and parallel. So make sure that you refresh your memory if you don't. We talked about it a couple days ago. But make sure you remember your rules for series and parallel. Yep. Please do. Now, in doing stepwise reduction, you're always trying to get yourself down to a circuit that has a single resistance. This represents the equivalent resistance of the circuit. Let's talk vocabulary for a minute. The word equivalent doesn't mean equal, doesn't mean total. It means equivalent. They're going to use that word more prevalently on the exam. Equivalent suggests that you could replace the entire resistor component with a single resistor of this value. That's what the word equivalent means. So I'm going to use the word equivalent as much as possible because that's likely how they'll write it on the exam. What is the equivalent resistance for this circuit? But we also know that it's connected to a 12-volt source, suggesting due to Ohm's law that I have 2 amps of current. Now, I'm skipping through the minutia of the math, but all you're really going to do from this point forward is use Ohm's law. So the voltage was 12, the resistance was 6. Pretty straightforward. If you think back to capacitors, I did the same thing, but I used the definition of capacitance. Same idea. So for you guys who didn't have a strong foundation in this last year, Ohm's law replaces what we used for capacitance when we did capacitor circuits 2 weeks ago. Now, this is the hard part, I guess, because there's nothing on your exam that's going to tell you this. There's no thing in the equation sheet. But when you go backwards from here to here, you have to be able to take with you and apply the part of this circuit that is the same here. And this is where Kirchhoffs laws are important. If there's no break in a circuit, then you know that the current can't split. So in stepping back to a set that's series, Kirchhoff's second law says that the current applies. Kirchhoff's first law would say that there's a voltage drop across each resistor. Doesn't necessarily say that they're the same. But Kirchhoff's second law says that there's no junction, then the current can't be split. Due to conservation of charge, if there's 2 amps through one of these, there has to be 2 amps through the other. Now, we ignore the equivalent circuit, go to this new equivalent circuit, and apply Ohm's law again. In this case, 2 times 4, it's going to give me 8 volts. 2 times 2 is going to give me 4 volts. The thing about solving circuits is your ability to check your work is pretty prevalent throughout. I had 12 volts before. I should have 12 volts still. The sum of the voltage drops has to equal 0. So the battery was 12 volts. Each of these voltage drops across the resistor has to take that 12 volts back down to 0. So my original battery, 12 minus 8 minus 4, 0. Questions about that? All right, so now we're going to go back again. Before I do, I recognize that the 4 ohm resistor doesn't change in this instance, so it's still going to be 8 volts and 2 amps. However, when I step back this time, I'm going to a parallel element. Based on Kirchhoffs laws, the current must be split, so it's not the current that's going to be the same for both of these. However, the potential difference from here to here must be. So I grab my 4 volts and apply it to each. Can then use Ohm's law again to figure out how much current must be passing through each of those resistors. So 2/3 of an amp here, 4/3 of an amp here. Again, you can check your work. There was a total of 2 amps going into the junction. I better have 2 amps coming out. So 4/3 and 2/3, 6/3, that's 2 amps. Questions about that? All right. Not too bad. We have, in effect, solved this circuit. However, that's usually not sufficient for what they're going to be looking for on the exam. They're going to be looking for something else. So there's a couple of, bless you, a couple of things I want you to make sure you understand. How much current is passing through the battery? I'm not trying to trick you. This one's an easy one. 2 amps. It's important to understand the terminology. That in the case of this particular circuit, no matter how complicated it is, the battery produces 2 amps. But that means that 2 amps is passing through the battery. Don't be confused by that language. They'll often say how much current is passing through the battery. The battery is a circuit element, so current must pass through it. Regardless of how it separates the potential, charges must be passing through the battery. So we would say 2 amps passes through this battery. Power, the last thing from last year. You should have had 3 ways to compute power from last year. Technically, power is voltage times current. Technically, this is the definition of power. But with Ohm's law, you get variations. Now, for a capacitor circuit, we didn't have power. For a capacitor circuit, we had the energy stored. So we talked about the energy in a capacitor, 1/2 CV squared. For resistors, we don't talk about energy stored. Resistors don't store energy. Resistors consume energy. But since there's a flow of current through a resistor, we don't talk about the total energy consumed when we solve a circuit. We talk about the rate at which energy is consumed. For those of you unfamiliar with the definition of power, which, believe it or not, we'll be talking about later today too, the definition of power is the rate at which work is done, or the rate at which energy is consumed. Power is dE dt or dW dt. It's a rate, so it's a derivative. Now, I do want to circle back to that. So I want to come back to talk about power, but for this circuit, there was 24 watts of power being consumed by the equivalent resistor. If I look at my circuit, there's 16 watts there. There's 8 watts there. And there's 16 watts there. The unit of power is the watt. So a volt times an amp is a watt. Now, just so you know, when it comes to checking your work, 16 watts plus 16 third watts plus 8 third watts is 24 watts. You can always check your work when it comes to resistor circuits. But be careful. There are a lot of students who think you can add up the voltages and they should equal 12. They won't. The power will equal the total, but the volts never will. On the other hand, get all those green circles out of there. Consider any circle through the circuit. Please notice that the voltage drops are 0 for any of them, right? 12 minus 8 minus 4, 0. If I do the outer loop, 12 minus 8 minus 4. Good so far? Now, this is getting pretty messy here. I do want you to look at this junction though, 2 amps in, 2 amps out. You see that as well, right? Let me redraw a piece of this on another page. Just a circuit. And assuming you guys have your notes in front of you, I'm gonna make this nice and big. So I have lots of room to work. "12 volts, 2 amps, 4 ohms, 8 volts, 2 amps. This was 6 ohms, 4 volts, and this side was 2/3 amps, and this one was 4 volts, 3 ohms, and 4/3 amps. I assume that most of you, in following along with this, recognize that the current was traveling in this direction through this resistor. No doubt? We all good with that? And the current was traveling through this resistor in this direction and through this resistor in this direction. We all okay there? The sum of the voltage drops in any closed loop is 0. Now we did 2 of those loops that were pretty obvious, but this is also a loop, right? That has to be a loop, and therefore it must obey Kirchhoffs Law. And I lied to you yesterday. I said that resistors always represent a drop in potential. That's a lie, a bold-faced lie, that I need to remedy right now. It was easy to tell that lie yesterday because I knew we wouldn't see a case where that wasn't true. I needed to make sure that we had walked through a couple of circuits first before we really talk about what's happening here. But it's not always safe to say that a resistor represents a drop in voltage. When you are tracing a loop through a circuit, you are making an assumption about the direction of the current. When you go against the current through a resistor, that must be an increase in potential. There's a drop in potential as the current passes through a resistor. So there's a drop in potential from here to here. But if my loop that I've drawn goes against the current, when I go from point A to point B, that's an increase in potential. So in this loop, if I was to draw it out and talk about Kirchhoffs Law, that would be plus 4 volts going across this resistor and minus 4 volts going across this resistor. Now you might be asking, why am I even bothering with that? It was pretty easy to determine what direction the current was in this circuit, wasn't it? I want to give you another circuit where maybe it's not so easy to figure it out. All right? The moment we connected that 2 ohm resistor there and transitioned this from being a set of parallel or a set of series to one that's neither, that 2 ohm resistor now draws current. Well, hello, Chase. When there was no resistor there, no current was drawn. But now there's going to be a draw of current through there. When you're faced with this circuit, you're going to have to figure out how the current is going through the circuit. You're going to have to make some decisions because your Kirchhoff loop has to take in every circuit element. It's real easy to say that this loop is going to have voltage drops across the 4 ohm and the 12 ohm. That one's easy, I think. And it's not so hard to take a look at this loop. That one's not so hard either. Pretty confident that there's going to be a voltage drop, a negative voltage across the 6 ohm and the 3 ohm. But what direction is the current going? I have not drawn a loop yet that takes into account the 2 ohm resistor. And the truth is I have like 4 different options. I mean, I could do a little loop here. I could do a loop here. I could do a loop like this. I could do a loop like this. Well, that's a mess. But what you need to understand is you don't know the direction of the current across the 2 ohm resistor. You don't know. So you don't know whether to add that voltage or subtract that voltage. So today we're in a little bit of uncharted territory. Although I taught you Kirchhoffs Laws last year, it was intentionally skewed towards problems I knew you could face without having to really use Kirchhoffs Laws. In the real use of Kirchhoffs Laws, you must assign a direction to your perceived current through every circuit element before you apply Kirchhoffs Laws. What that means is you go to each resistor and draw an arrow indicating what direction you believe the current must be passing through that circuit element. You decide. And you make that decision in order to know whether it's a voltage drop or a voltage increase. Now, in some cases, drawing that arrow is easy. Very likely you're going to be able to make an easy decision about it. But in some cases, it's an unknown. But here's the deal. The direction of this arrow doesn't matter in the long run. Pick a direction for it. Just pick one. If, when you are done with this process, the current through that resistor comes out positive, then you chose the correct direction for the current. If, when you finish this process, the current through that element comes out negative, then the current is in the opposite direction of the arrow you drew. All you have to do is make sure you have picked a direction. Your deciding reference. It's no different than saying where is 0 on a conservation of energy problem. It's no different than that. You are picking a point of reference. So I am choosing these as my reference points for the directions of all of the currents. And therefore, when I pick a loop through the circuit, I will always make my current and my potential based on the direction of that arrow. So, let's practice. Let's pick the easy loops first. My easy loop first. And I think I made sure that every single resistor was a different value. So I'm going to name the currents based on the value of the resistor. Is that okay with you? What I mean by that is this loop will be positive 18 volts minus the voltage across the 4 ohm resistor minus the voltage across the 12 ohm resistor, and that equals 0. Any question about that? Good to go on? All right, so I'm gonna erase this loop just so that it doesn't get in the way of drawing the next one. Again, I want to hit the easy ones. That loop now. Is that okay with all of you? So you guys can do that one on your own. You really don't need me. All right, we have to do something to get that 2 ohm resistor. And it doesn't matter where you go with this. It's going to be the same amount of work. There's no easy way. So I'm going to choose this path because this is what I feel like doing. And had you asked me, I don't know, tomorrow I might say something different. But let's go with... Okay? Now, based on the direction of the loop I've just drawn, I'm going in the opposite direction of the arrow through the 12 ohm resistor. So I add that potential, positive V12. Can you see that, or is that color not good? Jackson? Okay. The 2 ohm resistor, I'm going to point out based on the direction I drew the arrow, I'd have to add that voltage to positive V2. And now the 3 ohm resistor, minus V3. Our goal is to try and get the voltages right as much as possible. The signs are what's going to save us in this. But look, having decided on those current directions, the yellow arrows that are there, that is also going to be used in Kirchhoff's second law, because there's a lot of junctions here. Every one of these junctions represents a use of Kirchhoff's second law. This is going to generate 4 equations, one for every junction. And they are not all the same. Let's label this. I got A and B are labeled. We'll label that C and D. Let's do junction C first. Is that okay? You'll notice I did not draw an arrow through the battery. Let's go ahead and draw an arrow through the battery. I am going to label that I total. That is definitely the total current. So going into junction C is I total. Coming out of junction C is I4 plus I6. Everybody good with that? You guys told me to turn it up. Yeah.
So you're saying that the current for the at junction C almost like loops around?
No, I'm saying that the current here has to equal the current that comes out through that resistor and the current that's going to this resistor. It's not looping around so much as there's no break in the current. So whatever current is through that 6 ohm resistor had to be what exited along the top there. Okay? All right, let's hit a junction A. I see I6 going into A and I2 and I3 coming out of it. Junction B, I see I2 and I4 going into junction B and I12 coming out of it. And then junction D, I see I3 and I12 going into junction D and I total coming out of it. 1, 2, 3, 4, 5, 6, 7 equations. I know. Told you Kirchhoffs laws are the absolute hardest way to solve a circuit. And you did ask for me to turn it up a little bit. I'll remind you, you asked for this. I would have been quite happy with like 2 batteries and a resistor. You wanted something a little bit challenging, so here you go. A little challenging. Now, do you understand, though, at this point, we've done all the physics. There's a lot of algebra. And there's a lot of things here we can still put down. Like, look at the 4 ohm resistor. The 4 ohm resistor is V4 equals 4 times I4. Right, that's Ohm's law for the 4 ohm resistor. And for the 6 ohm resistor, that's V6 equals 6 times I6. You kind of know why I named the resistors the way I did now, don't you? So V12 equals 12 times I12. V2 equals 2 times I2. And V3 equals 3 times I3. Now your job is to figure out what all of those voltages and currents are. I mean, it looks terrible. Just awful. So, are you ready?
Let's do it. We're already here.
It looks rough, and to be quite honest with you, it is. If you want some advice, first, I said before, there are ways around this. Second, you would never do this on an AP exam. Do you know that we are 12 minutes into this problem? So this could not be an AP exam level question. This circuit is called a Wheatstone bridge. It is a classic circuit. It is used for this purpose, to teach the way in which a system can be set up to decide the direction of the current through a single element. This circuit is usually given a tunable resistor, where you tune it in such a way to balance the current through the bridge resistor. It's used for precise measurements of resistance. So this has a purpose. But to do the work, the first thing you should do is substitute all of the voltages for the currents. That should be your first step. Your next step is down here. Reducing the currents to the fewest number of currents. That's how this is done. There are no easy steps. This is going to produce a large number of systems of linear equations. Generally, you're going to get it down to 3. 3 equations. Because you have 3 voltage equations, that's where most of your substitution will go. And to try and reducing this down to those 3 equations, and then using some kind of system to solve that linear set of 3 equations. There's no shortcut around this math, though. None at all. The first thing I'm going to need is more room. So I don't easily have more room. So I would say 18 minus 4 times I4 minus 12 times I12 equals 0. And 18 minus 6I6 minus 3I3 equals 0. And 12I12 plus 2I2 minus 3I3 equals 0. Now you'll notice the first thing I've done is I've eliminated the voltages completely. And now I have 7 systems of equations with current, with 7 unknowns. That's where you start. Now you just got to start eliminating by using these substitutions. There's no shortcuts though. It's rough. the information that is right here. That's what they're holding. They're holding all of those equations are in the partial currents. So that instead of doing a substitution with 7 equations, let's get back to the original circuit. And this is not going to make it incredibly easy. It's just going to reduce the number of original equations. So here's our circuit again. And be kind, tell me out. Was it 6 and 3? And 4 and 12?
Yes.
And 2? And was it 18 volts? No. So what I'm going to show you is an interesting take on Kirchhoffs laws called the wire mesh loop theory or wire mesh loop procedure. It is not, hold on. So the wire mesh loop theory. To do the wire mesh loop theory, we're going to kind of combine both laws at once. Okay, so to do this, and I would use the loops I'm going to choose, but understand that the rule still applies. You need a loop that encompasses every circuit element. So I'm going to do and draw 3 loops. I'm going to label them. And it doesn't matter what direction you draw these loops, just make them easy to read and make the arrows easy to identify. So I'm going to change the color for each loop. Okay. Now, what this process will do will create 3 equations and 3 unknowns. Because you will get basically 3 loops. And each loop will be its own equation. Now, this only works for resistor circuits. That's the drawback. So every one of these ways around around Kirchhoffs laws has a drawback. That's this one's drawback. So we're going to combine all 3 rules, Ohm's law, Kirchhoff's first rule, and Kirchhoff's second rule, all at one time. Now, this part's important. We're going to take and draw out the equation for loop A. Here's how it goes. You're going to walk around this loop. Every time you encounter a voltage supply, you'll simply add the voltage supply in. We're always going to draw the loops so they're in the right direction for the voltage supply. But the rules for the voltage supply still work. If you go little side to big side, you add the voltage. Big side to little side, you subtract the voltage. When I encounter a resistor, I'm going to put the negative sign in. I am going to subtract every resistor. But instead of putting the voltage for the resistor, I am going to, at one time, combine Ohm's law at the moment that I hit the resistor. And instead of doing IR, for I, I'm going to look at the 2 loops I just put in there. I'm going to look at the resistor and any loops passing through it. There can never be any more than 2 currents passing through any one resistor when you draw your loops out. What I mean by that is I have loop B and loop A both traveling through this 4 ohm resistor. Do you guys see that? Since I'm traveling along with loop A is positive. That's the positive direction. So when I look at loop B and notice that it's going in the other direction, then I say from the vantage point of loop A, B is negative. And in the parentheses, I will write A minus B. Okay. I know it doesn't make a lot of sense this second. Just keep following. Then multiply by the resistance, so times 4. We keep chasing my loop. The next resistor I come to is the 12 ohm resistor. Again, I'm going to use Ohm's law. I'm going to open up parentheses for the current. And I'm going to write times 12. For the current, I have A. But now I notice that there's also C passing through it. You guys see that all right? So I'm going to do A minus C. I go back to my power supply now. I've completed the loop. I set that equal to 0. Now, if you're a mathlete, you're probably noticing that this is going to generate a relationship for each loop, but the only variables I will have will be A, B, and C. I will have 3 variables. These variables don't represent the current. They represent false currents. The actual current through the 4 ohm resistor is A minus B. The actual current through the 12 ohm resistor will be A minus C. Those will be the actual currents. What we're finding is what this law refers to as partial currents. They're not real. These are not real currents. They're a construct. They are doing a substitution with 3 equations, and at the end, I'll use these values to determine the individual currents. It's a lot easier. I know it doesn't sound it yet, but let's go to the next one. Let's go to B. Notice there's no power supply in B, but B becomes the positive direction. So the first thing I encounter is the 4 ohm resistor. So for B, it's going to be negative, open the parentheses up, B minus A times 4. Yep.
So why do you put a negative in front of the
Resistors are always voltage drops. Go to the next one. The next one's the 6 ohm resistor. You guys see that? The only current passing through it is current B. So that would be B times 6. Go to the next one, the 2 ohm resistor. So minus, open my parentheses up, there's 2 currents. It's going to be B minus C times 2. We good? Any questions? Can you do C on your own? Try it. I'll verify in just a minute. All right, so you should be done. It doesn't take that long to do this once you see it a couple times. So minus, and you had C minus A times 12, minus C minus B times 2, minus C times 3 equals 0. We good? All right, now look. You have 3 equations and 3 unknowns. You see that, right? So that's all you have to do now is solve this equation. Now, there's a system of 3 linear equations, but we can simplify it too a little bit. I have negative 4A and negative 12A. I'm looking at simplifying equation A. And right away, I see that I have 18 minus negative 4A, negative 12A, so that's negative 16A, positive 4B, and positive 12C. Equals 0. Do you guys see what I've done? Jake?
Probably a dumb question.
Probably not.
What are you solving for? When you solve for those variables?
When I'm done, I want to solve for A, B, and C.
Yeah.
So when I get A, B, and C, which I'll have some number for it, the current through the battery is going to be current A, because it's the only current passing through the battery. The current through resistor 4 will be A minus B. You follow me? Because both of those currents pass through that one. The current through resistor 12 is going to be A minus C. The current through resistor 2 is going to be B minus C. And the current through resistor 6 is going to be B, and the current through resistor 3 is going to be C. That's what it'll do. It's so much better than having whatever we had earlier, a lot of variables. It's faster, and the best part about it is it generates a straightforward system of equations that can be solved with a computer. This is how you program a computer to solve a resistor circuit, because computers are great at solving linear equations. Humans, not so much. I would argue that you guys are probably not great at this. Like when we get this done, and I want to get one more step. So let me just get the other two equations down here. So follow along. I've got B in all three of those. I have negative 4B, negative 6B, and negative 2B. So 4 plus 6 plus 2 will be negative 12B. Let me put that here. Negative 12B. I see that I have positive 4A, and I have positive 2C. Then for the last one, I've got positive 12A, I've got positive 2B, and I've got 12 plus 2 plus 3. So 18C. Is it 17? Yeah, I'm sorry. That sucks. It's nicer when it was all even.
Yeah, it is the one guy.
All right. Now, the process of solving a system of linear equations, I don't know, you guys good at that or bad at that? Which one do you guys know how to do? Sure, it's easy when it's two. Did you guys learn what, row echelon elimination? Kramer's rules?
Substitution elimination and
Wow. So you guys really have not learned. They're relatively straightforward, but in these kind of contrived examples, you're going to likely be given quite a bit of information. So in this one, we're missing two resistors. The question probably would be, what's the current through one of the resistors? Something like that. So with Kirchhoffs rules, start with a loop. And so I'm going to say there's a loop through the circuit. I know the voltage drops have to sum to be 0. Unfortunately, that loop doesn't tell me very much because I don't know the voltages across either resistor. I just know there's 70 volts at the beginning. So starting with that loop, probably not great. So let's find another loop. How about this loop? When I look at that loop, I notice that I have two voltages in that loop and the 70 volts in that loop. The sum of the voltage drops has to be 0. So 70 minus 30 minus 20 leaves 20 volts, suggesting that there should be 20 volts here. So the sum of the voltage drops will be 0. You newbies, you guys seeing what I just did? So if you guys who were not doing this last year, this is a quick way of kind of demonstrating whether you know Kirchhoffs rules or not. So you all see where the 20 volts came from, right? Any question about that? Okay, so we go on to, say, another loop. And I start with loops. You could also try and start with the currents. We could have started with the currents here. Look at the currents for just a minute. Going into this junction is 4 amps. You see that, right? Coming out of this junction is 3 amps. That means this has to be 1 amp. Still all right? In fact, now if I go back to this loop, I know this has to be 50 volts. right? So that suggests this is a 50 ohm resistor, right? 50 volts, 1 amp. When I would do this with students in AP Physics 1, I tell them to treat this as if it's kind of a puzzle, because you're trying to figure out, what pieces do you know, what pieces don't you know. So look in places to see if you can kind of figure it out. Like I have 20 volts and 10 ohms on that one resistor. You guys see the one I'm talking about? Right here? Sorry, right here? Well, that means that there's got to be 2 amps passing through that resistor. And I have 3 amps coming into this junction and 2 amps coming out. That means this has got to be 1 amp over here. In fact, if I look at this big loop, I notice I have 70 volts, minus 20, minus 30. That leaves 20 volts over here. So this resistor had to be 20 ohms. You guys see what we're talking about now? So you guys who are new to it, I think probably should practice. And you guys who did this last year, I bet you could benefit from some practice. So let's benefit from some practice. Give her a shot. I think that's 40, not 46.